Next, we'll invite Josh to tell us a bit about the work here in New Mexico with water management, working with the state here. Josh is a member of the OpenET science team and has been one of the founding members from OpenET. Josh is also a climate scientist focused on terrestrial ecosystems, water, carbon, and nutrient cycling using a combination of remote sensing, high-performance computing models, and field campaigns, working from the Amazon to the Arctic. Completed his undergrad and graduate degrees at Berkeley and postdoctoral work at Oxford. And Josh, for a long time, was the scientist at the Jet Propulsion Lab in Pasadena, where he was the founding science lead for EcoStress, which is still flying on the International Space Station. And he's currently the science lead for Hydrosat and an associate professor of environmental science at Chapman University. So let me bring up the slides, Josh. It's not working. Let's see. Where did Rachel put event support? That would be a good place to look. You think it's under rigging or lighting?
Lighting. Clash the IT.
Oh, they're all loaded at the bottom. I just had to, thank you so much. I know, way too easy.
Okay. All right, thanks. Right, so my name is Josh Fisher. I do a lot of work on ET, working with OpenET, launching satellites to space. Also do a lot of work with the state of New Mexico, and I figured since we are in New Mexico, I will tell you a little bit about it. And some of these slides are borrowed from a presentation I gave to a NASA meeting that Forrest was heading up, and he also asked for people to give jokes. So I'm carrying over a joke. So I figured I have to come up with a joke about evapotranspiration. So the joke is, how do plants feel about the soil moisture they used in evapotranspiration? It will be missed. Okay, all right. So I will stick to my day job. That was clear. When I gave that joke to you last time, I was remote and I couldn't hear groans or laughter. It was just crickets. So it must have been groans. It was all groans. Okay, there we go. So this is reporting on a NASA-funded project. It actually has it's transcended a number of years in different forms of funding through NASA. Started off as part of an internship program where actually before that there was a Western States Water Council meeting at JPL when I was at JPL, and John Longworth, who is representing New Mexico there, came up to me after I gave a presentation on ET, and he said, we could use some of that for the state of New Mexico. And so we got an internship, or a set of interns, to work between the Office of the State Engineer and my team at JPL. And then eventually we got the funding through the NASA Western Water Applications Office, WAO, which Forrest was part of, and then more recently through the NASA Applied Sciences Water Resources Program, again, which Forrest helps manage. So the Office of the State Engineer in New Mexico is responsible for the appropriation and distribution of surface and groundwater in New Mexico. And so over the years, we developed a number of tools, data sets, platforms for use, but they were always housed at NASA. They were always housed with us at JPL. And really, the idea of the Applied Sciences program at NASA is to move those tools into operations by the end user and not have a reliance on NASA, which is easy to say, hard to do. And so that's what a lot of this work is entailing. And it's not kind of super sexy science and engineering. It's a lot of just kind of figuring out, permissions and who has rights to access data and transfer stuff from NASA to OSE and things like that. So New Mexico is a great state to work with. I love New Mexico. I used to come here all the time before the pandemic. This is my first time back since, so I'm getting my green chili infusion. But it is very dry and also not necessarily as rich as California, and all the brilliant lawyers that come out of it, and scientists. So within New Mexico, we categorized decision-making contexts into kind of three broad categories. One focused on drought response and mobilization, one on forest and wildfire monitoring, and another on agriculture and water management. And so the Office of the State Engineer works with a lot of state and federal, local partners and so on. And so part of that was kind of mapping out the decision tree and how ET data or thermal data can be used in various decision making. So I did a lot of traveling of the state, especially with Gregory Halverson at JPL, and meeting up in Santa Fe, and all the way down to Cruces, and so on, and just trying to figure out how the data can be used in the different decision-making contexts. And we drove around with folks like Matt Nelson, who's here, and Julie Valdez, or her predecessor, Molly Magnuson. And we would just drive around in the car and tether the phone to the laptop and pull up ET data as we would pass by different areas, and just kind of show the OSE team what we were looking at from space, which was a bit mind-blowing when they hadn't actually had a great picture of this. This was before OpenET as well, just to be able to do that in the car on the way and give them just direct data, which was pretty fascinating. We developed a number of what we called application traceability matrices, where we basically figured out what was the decision, who were the responsible kind of contacts and parties, what were their data requirements, what resolutions did they need historical, future, near real time, what kind of temporal resolutions, how do they want their data delivered, like raw data, just maps, and so on. And what were those potential impacts? That was something that NASA was particularly interested in. Could we put a number on how much money or how much water or wildlife can be saved or gained or improved through this, which is hard to do, but we started moving on that direction. One of the big things that we did for the state was that they wanted a long historical record to really look at consumptive use and historical use to really figure out if people were using water. And that was very hard for them to do, and also hard for people who were trying to sell or move their water rights around to establish to the state when, they were kind of not always well metered, and oftentimes the state was using, anecdotal evidence, or sometimes they were using just like pictures from tourists out of airplanes to see like what was going on. So this was definitely not the most efficient way forward. And we're like, well, we've got a very consistent way forward. So we developed about 7 terabytes of data, wall to wall, New Mexico, for about 30 years of ET data for the state. And so this is a good complement to what we're doing at OpenET, which has this great interface, but doesn't necessarily have the 30-year record yet. But we will get there. And so we did this using the evapotranspiration model that I had been using pretty extensively, called PTJPL, and it's also part of OpenET. So it was originally a global model, actually, kind of for historical contests. You probably heard a lot about I don't know what the first ET model you heard of, maybe was Blaney Criddle or something like that, but in terms of the OpenET models, probably Metric, because Rick was so active in the region, maybe Martha's Alexi. I was working at the global scale, doing global climate change, climate science, and so there was actually a kind of a dichotomy of scientific groups, of like those working at the very local scale and those at the global scale, and we knew each other existed and were friendly, but we had never been able to kind of compare our approaches until OpenET. And so from a scientific perspective, that was really exciting, because I had no idea how PTJPL was going to compare against, potatoes in Idaho relative to Rick's model that was designed for potatoes in Idaho. And it turned out that my global model actually did quite well. So we launched EcoStress. I was the science lead for that. That went to the International Space Station. It produces ET from there. You can download that as well at pretty high resolutions and frequency. And it uses PTJPL as well, and dyslexia, actually, now with Martha. And of course, it goes into OpenET, which you've seen a lot. So I think there's been a lot of focus on, I've heard a lot of talk about all the models except PTJPL. People say, oh yeah, SIMS is good and bad, and eMetrics is good and bad, and CVOF is good and bad. But like nobody ever says anything about PTJPL, because it's like, always just like right in the middle. It's just kind of like under the radar. But it does a pretty good job. So yeah, here we are from the paper, from Forrest's paper, showing where it hits against the other models. And what is also remarkable, extremely remarkable, we always talk about, oh, is it like 11% uncertainty or 10? Oh, if it's 11, then we're like totally screwed. But the fact that all these different models are so similar, and they have a lot of different assumptions and I'm more than happy to talk to you about all those differences. But the fact that they actually have come together is extremely remarkable in terms of the scientific literature, and that's a testament to what Forrest and our team has built for standardizing and unifying these models together. As part of our work with OSE, we also realized that there was great demand for open water evaporation. We talk a lot about agricultural, consumptive use, and so on, but I think Jordan and Jim this morning talked about, the hierarchy of water loss, and reservoir loss was like right after agricultural use. And so, I had a question to them. I was like, how are you guys doing that? Because before, we were actually just masking out open water evaporation because I didn't know how to do it. I was focused so much on plants. But when dealing with OSE and partners in demand, they wanted open water reservoir evaporation, lake evaporation. And so we figured out how to do that, and we implemented it. So that is part of our data set for the OSE now. And it's also in OpenET, I think. Yes. Right. Yeah. Is it the only one that does?
No, I think there's a couple.
There's a couple do it. Yeah. But that was born out of work with the Office of the State Engineer. So we have a few different flavors, actually. So we have a Landsat level product where it's high resolution for multiple decades. We also have this daily kind of coarser scale resolution from MODIS, also using PTJPL. And that's kind of easy access where you want the whole state. You're not interested necessarily in some specific part. And so it just makes the data a little bit easier to handle. In addition to the ET, we have an evaporative stress index, or a drought product, where it shows the ET relative to the potential ET. So that kind of like how much water is there relative to the atmospheric demand, and that is an indicator of drought, or evaporative drought, or vegetative stress. And so this has been, we've been working with the state climatologist, Dave Dubois, who's at the meeting, and Andrew Mangum at NOAA, National Weather Service. And they use the U.S. Drought Monitor a lot. And so when they're driving around their state or looking at the state to try to figure out if the state's in drought conditions, they're using the Drought Monitor. And here's an example from Curry County. And this is what the U.S. Drought Monitor gives you on top. One value, one color. And so as a state climatologist and the Drought Task Force and all the drought decision makers, what do you do with that information? And if you look at the evaporative stress index product that we create at a much higher resolution, it gives you a lot richer information in terms of what's going on, who's impacted, is agriculture impacted, are the forests impacted, is the riparian zones, is the uplands, it just gives you such a greater wealth of information for these decision makers to understand the drought conditions. And so Andrew Mangum and Dave Dubois are quite excited about this data as well. We also have found that our evaporative stress index data predicts drought before the U.S. Drought Monitor, up to 4 months earlier. So it's a great predictive tool, which we're quite excited about, and we're pushing forward with that scientifically. And part of it is because the U.S. Drought Monitor is too much of a one-size-fits-all. It integrates just every possible bits of information, and so integrates groundwater information that we don't integrate. So it's useful for some context, but there are complaints that the same method that's applied to Florida is applied to New Mexico, and that's maybe not the best way forward. Also, using our thermal data, we can actually get wildfires. So we can pick up those wildfires using the thermal data. So we talk about in this meeting so much we use the thermal data to get ET. We can also use the thermal data to pick up wildfires. And again, back to that evaporative stress, we can pick up that forest stress in as much as the agricultural stress. And this forest stress is an enormous predictor of forest spread. Where the forests are stressed, you have the wildfire spread, and you have more intense fires. So it's this great predictor of wildfire presence, absence, spread, and intensity. Finally, for water rights and water management for the state, we've developed a tool, a visualizer, where the state can upload different shape files of interest that they want to pull data from for this 30-year record, and then it pulls from that record and gives you that whether or not water was being used or not, and both seasonally. And so this interface was co-designed with the team in terms of exactly how they wanted it. But it's remarkable because right now, if there's an application going in to transfer water rights, the applicant and the state have to figure out, was it used historically? And now we've got, here's an image from 2018, 1999, 1988. So like a 30-year record, and it shows, yes, water was being used, or no, water was not being used. So it's very consistent, and it just streamlines that whole process. We've also done a bit of a preliminary impact assessment to see, based on historical decisions by the state, how often did they get it wrong relative to what our data are showing, or how often did they get it right? And they've done actually a pretty good job, but our data can help. So as I said, a lot of this was built on JPL supercomputers, and so now how do we get it off NASA supercomputers onto a state agency laptop? So we're going through AWS cloud, so we basically set up an AWS system, Amazon Web Service system, cloud system at JPL. We mirrored it at OSE, and we kind of have been like developing them in parallel and transferring them off. And that's where we are today, is literally today, data are finally being moved off the JPL server, or off the AWS to OSE's AWS, and we're setting up the web UI. We also have a big training and education component for the state. And so on my team, I have a designer, a human-centered design specialist at JPL. He does a lot with working with like astronauts and how they like learn how to use complicated instruments on space shuttles. But we can use that kind of stuff to also help state employees and collaborators use the system here. So we've got a training protocol, different videos, and I've had a number of my students at Chapman work on this as well. So they get to be involved in kind of important cutting edge research. And in every step we do, I'm big into traceability matrices. For every step, why did we do that step? Why do we make that decision? And how do we trace its efficacy or its effectiveness? So NASA likes to pull together lots of these testimonials, and so we've got quotes from like Andrew Mangum says it's really powerful telling data. We've got quotes from the OSC talking about how transformative and a game changer this is for them. So that's good. Also, as part of the impact assessment, we are looking at how to extend such tools to other states in partnership with OpenET and everything else that's going on. So we had started this a number of years ago using Landsat data. Then we launched EcoStress, and so then started including EcoStress. Then we got OpenET up and coming, and now OpenET is up and coming. And so there's always something on the horizon. And what's on the horizon? It's HydroSat. So that is, I'm no longer the science lead for EcoStress. I'm now the science lead for HydroSat, and we're launching a constellation of essentially Landsat-like thermal instruments. So instead of 100-meter thermal every 16 days, we're actually getting 50-meter thermal every day, or multiple times a day, in addition to 20-meter visible and near infrared. So previously, you might have your once every 16 days thermal data, and then in between this is being slow, your kind of blurry MODIS level data, and so now HydroSat is coming in and sharpening that up for every day. And so hopefully we can infuse these data into OpenET as well. So we have an early adopter product now. It's 20-meter thermal from a kind of a spatial fusion data, but our actual first launch of the constellation is in July. So we're very excited about that. So that should hopefully be game-changing. And with that, that is a little bit about some of the work I've been doing and relationship to New Mexico. Thanks. Happy to take questions.
Thanks so much, Josh. We can take one question. There's a question for Josh. Okay. Since we're, one in the back, yeah. So the question was, have we observed changes in evapotranspiration and consumptive use as a result of increased production of cannabis and associated water use?
Yeah, I don't have a good answer to that, mostly because that's kind of the line where I hand that data off, and then the OSC folks start asking that or answering that exact question. In it, cannabis or pecans or droughts or and deforestation, all those questions are asked with that. So those are the type of questions that are being answered with these types of data. But that's where I hand that off. I don't know if any of the OSC colleagues are.
I tried to ask this question in another forum, but is there any synergy that you see between the now developing open topo, which is going to be using the digital elevation models, and I believe we're talking about 60 or 30 millimeter resolution of ground surface. So we're talking about a very high resolution in places that want to go ahead and spend the money, and California is one of them. And so you have this elevation model now, and now can you use that with the other remote sensing technologies and methodologies to actually bolster the pixels?
Yeah, that's a good question. I mean, the broader question is, we presented all this, from OpenET and my project here. Where do we go from here, right? And so we're like, oh yeah, 30 meters is great, but it could go better. And so hydrosat's going up, and both spatial and temporal. We can go higher resolution. It's just a matter of like computational cost for processing it. But now that we're set up either on with Google or on AWS with the cloud, it just becomes a lot easier to do that. So we can incorporate higher resolution topo, higher resolution thermal, higher resolution visible near infrared, and so on, meteorology if that was available. We just have to process it again, reprocess the data again. And that costs a little bit of money to Google, costs a little bit of money to Amazon, but it's doable. Yeah, it's definitely doable.
Thanks so much, Josh. Appreciate the thank you. And I know we'll be watching the launch of Hydrosat closely and hoping for all the best. And then especially the work on the evaporative, demonstrating the value of looking at evaporative stress index is a really nice benchmark as we look at producing historic archives for the West through OpenET as well. So thank you for that.